positive charge sitting out in space, it's going to create an electric field, and that electric field is going to point radially outward away from the positive charge. And you might know that if you've got a current in a wire, that current is going to create a magnetic field, and that magnetic field is going to loop around that wire. It's going to look something like this. But people started to realize there's another way to create a magnetic field besides having a current, and there's another way to create an electric field besides having charges. Turns out if you have a changing electric field in some region of space, even if that region has no current in it, by the fact that it has a changing electric field, that's going to induce or create a magnetic field. So here was a way to create a magnetic field that didn't even require a current. It just required a changing electric field in that region. And people also started to realize if you've got a changing magnetic field, that is going to create a changing electric field. And a very clever Scottish physicist named James Clerk Maxwell realized, hold on, if this is true, if a changing electric field can create a changing magnetic field, then a changing magnetic field could in turn create a changing electric field, which could in turn create a changing magnetic field, and you can set up some sort of chain reaction here that can propagate like a wave, and you would get a wave of electric and magnetic fields that can travel outward and have sort of an independent existence now from whatever parent current or parent charge created them. So how would you create a changing electric field? You could take this charge and sort of wiggle it upside down, up and down. Sounds like an antenna. That's what you could do in an antenna. That would create a changing electric field and then a changing magnetic field, and this could propagate outward. And similarly, you can have a current. How could you create a changing magnetic field? Just have this current oscillate back and forth, changing. That would create a changing magnetic field, which would create a changing electric field, and it could propagate outward, and now this wave could have its own independent existence and keep moving forward at some speed. And we call these electromagnetic waves because electro, they have electric fields, and magnetic because they have magnetic fields, and waves because they propagate outward according to wave equations and similar to all the other waves that we've seen. There is one difference. These waves don't actually need a medium. They could travel through straight vacuum. You don't need actual particles of some stuff in here. These can move through the vacuum, which is a little weird, because the only thing that's waving here, the only thing that's oscillating is the value of the electric and magnetic fields. And so these are electromagnetic waves. This is a pretty horrible drawing of it. Looks a little bit more like this. These yellow lines represent the magnetic fields. These are directed up and down. They point up and down. They don't stick out up and down. I just have to draw it that way, but what I'm trying to say is that this point right here, it's not that there's a magnetic field that sticks up, it points up. And I just draw it with a bigger vector to show that at this point right here, along this axis could be, say, the x direction. So if this is the x direction, then at this position in space, there would be a relatively large magnetic field, it would point up. And these red lines represent the electric field. So at this point in space, there'd be a relatively large electric field, and the electric field is at a right angle to the magnetic field. So these are perpendicular. That's how this process has to happen. It's going to create an electric and magnetic field that are perpendicular to each other. So the electric field sticks out. This is pointing, think of it as out of your computer screen or your screen, whatever you're watching this on. And these electric fields back here point into the screen. And so this is in 3D. This is happening in 3D. Electric field oscillating into and out of your screen. Magnetic field oscillating up and down. And the whole wave traveling to the right. So this whole thing happens. All three of these directions are at right angles. So if I imagine a three-dimensional axis here. So X, Y, Z. This would be the direction of the speed of this, or the velocity of this wave. It doesn't have to point in this direction, but whatever direction it's pointing, you'd have velocity in one direction, you'd have magnetic field in the other direction, and you'd have electric field in one more perpendicular direction. All three of these are perpendicular to each other. So the magnetic field is perpendicular to the electric field, electric field perpendicular to the magnetic field, and both the magnetic and electric field are perpendicular to the direction that the electromagnetic wave is traveling. And the speed at which these waves travel is the speed of light, c. And by c, I mean 3 times 10 to the 8th meters per second, because light is just an electromagnetic wave. Light is a special example, one particular example of electromagnetic waves, but it is only one example. These waves can have any wavelength. Look, from here to here. Since this is in space, a graph of the wave along a spatial direction, this would represent the wavelength. These waves could have any wavelength, any particular wavelength, and any particular frequency. The frequency would be the rate at which these change. So if you'd watch this in time, this point in space would have a magnetic field that would point up, then it would point down, then it would point up, and then it would point down, and the rate at which that's happening, the number of times per second, would be the frequency. These waves could have any frequency, but for one special region, the region is the visible spectrum. So we call the region of frequencies and wavelengths that electromagnetic waves can have the electromagnetic spectrum, and there is a lot to learn about the electromagnetic spectrum. Let me just show you really quick. If we pretend we're graphing here, along this line, higher frequency. So let's say in that direction, this is pointing higher frequencies to the right. In other words, higher hertz, since that's what we measure frequency in. But if that's higher frequency, because of this formula, speed of a wave is lambda times frequency, wavelength times frequency. If the frequency increases, the wavelength has to decrease. So in this rightward direction, this would be smaller wavelength. And wavelengths measured in meters, but when you're talking about light, since you have such small wavelengths, you often talk about nanometers. So where would the visible spectrum be? The visible spectrum would just be this little smudge here in our range. This would be this whole thing is called the electromagnetic spectrum. So the electromagnetic spectrum, and the visible spectrum is just right here. This would be the visible spectrum. So this is visible between red and violet. And red is, if I ask you what frequency that is, that would be around 4 times 10 to the 14th hertz. And violet would be around 7.5 times 10 to the 14th hertz. Or if you wanted to talk about wavelength, red would be around 750 nanometers, and violet would be around 400 nanometers, and by nano, we mean 10 to the negative 9th. Okay, but this is just a small region. You can have higher frequencies than violet, and what do we call those? We call those ultraviolet. And we know these are bad for us. And they're bad for us because as we go to the right here, higher frequency, turns out this also means more energetic light. So if you were to talk about the photons that make up this light, if you're talking about it quantum mechanically, those photons as you go forward higher up into the frequencies have more energy. That means they're more dangerous. And they're more dangerous because if they have more energy, they can add that energy to your cells and break them apart and cause damage. And so this causes problems as you go further out this way. So we put on sunscreen to protect ourselves from ultraviolet light. But this isn't the highest frequency. You can have much higher frequencies. You can have X-rays. X-rays are even higher frequency, even more dangerous, which is why X-ray technicians, you go in there and they're like, hey, stand right here. I'm going to get your X-ray while I hide behind this wall, because if they had to sit there and take that X-ray every single day, it would really be bad for them. But this isn't even the highest. You've got things called gamma rays. And gamma rays are unbelievably energetic light, and these are very dangerous. These come from space or from some sort of nuclear reaction. These are extremely dangerous, gamma rays. That's why you always hear them in comic books. When people want to blame like why some hero was created, they say, oh, that was a gamma ray, because it just sounds really powerful. It won't turn people into superheroes, but it's very energetic. Then down here, you've got infrared. So this would be below red. You couldn't see this either. It'd be infrared. And then below that, you've got microwaves. And microwaves, in this region, there's lots of useful stuff. Your cell phones, signals are in the microwave region. TV signals that are sent through the air in the microwave region. This is used for a lot of cases. And then below this, you've got radio waves. Even though, technically speaking, FM radio waves are more in the microwave region, these are more like AM. So when people started first making radio, they used frequencies down here, and that was the AM frequency range. So this is the electromagnetic spectrum. The visible range is a small region of it. We can't see anything outside of that, but these are extremely useful in a lot of different cases and dangerous, so you need to know about the electromagnetic spectrum.